Ladies and gentlemen, may I have your attention, please? Our next parallel session is about to begin. Please take your seats. Once again, our next parallel session is about to begin. Please take your seats. Thank you.
Our next speaker is Thiago Bergamaschi, who's going to tell us about quantum advantage from Gibbs sampling at finite temperature. Let's welcome him.
Hello. Hi, everyone. Thank you all for tuning in. Today, I'll be talking about our work titled Quantum Computational Advantage with Constant Temperature Gibbs Sampling. And this is based on joint work with Anthony and Yunchao. And I'll also be presenting elements of a follow-up work by Rajakumar and Watson. So our work, broadly speaking, is on the complexity of quantum Gibbs sampling. So in thermal equilibrium, quantum many-body systems described by some local Hamiltonian are expected to lie in their Gibbs state, which is the following matrix exponential. The process in which a quantum system converges to its Gibbs state is known as thermalization. And this thermalization process defines a natural, physically inspired model of computation, wherein one first couples the system of interest to a large thermal bath at some fixed constant temperature, and you simply just wait for it to thermalize, eventually converging to the Gibbs state. The dynamics of this process is driven by a so-called thermal Lindbladian, in particular, or most notably, the Davies generator, which we might have heard about earlier. And the concrete question that we try to study in this work is there some meaningful notion of quantum advantage that we can achieve in this dissipative model of computation? Great. So before actually diving in, I wanted to spend a few words to ask what makes this challenging. And essentially here, there's two conflicting points of intuition. The first is which, at high enough temperatures, sampling from quantum Gibbs states is essentially a classical task. In particular, you might want to leverage techniques such as cluster expansions or other structural properties. And here you may recollect the recent unentanglement line of work. Conversely, at low enough temperatures, this task, or Gibbs sampling, is expected to be hard in general, even for quantum computers, or in particular, NP hard via the celebrated classical PCP theorem. So in some sense, searching for Hamiltonians which are both classically hard, but easy for quantum computers is something of a sweet spot in the middle. Great. So with that in mind, I can introduce the task that we study. Given some local Hamiltonian H, and some fixed inverse temperature, or constant inverse temperature beta, the goal is to approximately sample from the distribution given by measuring the Gibbs state in the computational basis. Is that somewhat clear? So with that in mind, our main result is the following theorem, which says that there exists a family of n-qubit constantly local, or like k-local Hamiltonians, and some fixed inverse temperature beta, which is both rapidly thermalizing, and in particular, you can sample from it efficiently on a quantum computer, and moreover, classically intractable under standard complexity theoretic assumptions stemming from the literature of random quantum circuit sampling. Great. So this very nice follow-up work by Rajakumar and Watson tried to understand the setting where the Hamiltonian was constrained to also be geometrically local. And in particular, there they showed that you could actually find 5 local Hamiltonians lying on a 3D lattice, which had similar properties. They were both rapidly thermalizing, and they were classically intractable to sample from up to an inverse exponential error. And here, all they really relied on was a much weaker complexity theoretic assumption, like the non-collapse of the polynomial hierarchy, which I might get into later. So with that in mind, I wanted to briefly discuss a broad picture of our approach on how we get to these results. And broadly speaking, the goal is to engineer some family of local Hamiltonians which is both classically intractable by embedding some hard quantum computation into its Gibbs state. Now, this already poses some challenges because generically, quantum Gibbs states are typically noisy versions of their ground state. And yet, typical means to embed hard quantum computations into local Hamiltonians embed them into their ground state. So however we perform this circuit to Hamiltonian mapping, there will have to be some ingredient of fault tolerance to it. And simultaneously, we'd like this process, or like this Hamiltonian, to be rapidly thermalizing. In other words, a sublinear or polylog n time bound on some like mixing process. And in general, this can be quite challenging, even for commuting systems. And most recently, there's been a very nice line of work on some high-temperature non-commuting systems. Great. So what do our Hamiltonians look like? It turns out that the family of Hamiltonians that we study are the parent Hamiltonians of shallow quantum circuits. So to define this family, let's start with some simple the simplest non-interacting system, which is a sum of single qubit Pauli Z operators. And then we consider the class of Hamiltonians given by conjugating this non-interacting system by a low-depth circuit C. Now, this family of Hamiltonians is well known to have a series of nice properties. In particular, they're local, where the locality of the Hamiltonian is bounded by a function of the depth of the circuit. They're commuting, and they have integer spectra, both properties that they inherit from the non-interacting system. And crucially, the ground state of the Hamiltonian is the output of the circuit acting on all zeros. What is non-trivial, however, is that the Gibbs state of these Hamiltonians actually resembles a noisy version of the circuit under input noise, or input bit flip noise. And to see this, it's actually quite instructive to write out a short calculation. One can begin by looking at what the Gibbs state of the non-interacting Hamiltonian is, and we just get a simple tensor product. And this tensor product is a series of diagonal matrices, which we can actually interpret as noise on the input. And subsequently, we just conjugate both sides by the circuit using the convenient identity on the top right-hand corner, which says that conjugating a matrix exponential by a unitary is equivalent to conjugating the exponent. So in this context, we can write out the Gibbs state as applying the circuit to a layer of stochastic input noise. Great. So what's convenient about this is that it already gives us a recipe for finding Gibbs states which are hard to sample from. It suffices to engineer a family of shallow quantum circuits which is hard to sample from under input noise. Unfortunately, this input noise model isn't that well studied in the broader context of quantum error correction, but nevertheless, there's this very elegant work by Bremner, Montanauer, and Shepard who showed that many families of classically hard shallow quantum circuits actually become classically simulatable if you add just a tiny bit of input noise or any constant amount of input noise. And so this kind of justifies my previous claim that we need some form of fault tolerance to our mapping. So this brings me to the outline of our technical contributions, which consists of two parts. The first part is on designing efficient Gibbs sampling algorithms for these local Hamiltonians. And here we prove what's known as a log Sobolev inequality for this family of local Hamiltonians, relying on careful circuit light cone arguments. And in part number two, the second main technical contribution, is a fault tolerance theorem for shallow IQP circuits, where we show how to design fault tolerant circuits which are still hard to sample from, so long as the noise model is constrained to stochastic input noise. And here the whole goal is to minimize the time overhead of the fault tolerance construction. In the interest of time, and in this talk, I'll try to focus on the main proof ideas behind the first part on the efficient Gibbs samplers, although I'm happy to take questions on the fault tolerance component as well. Great. So to set up some background, fortunately I can rely on Cambyse's previous talk. Our algorithms are based on studying the so-called Davy generator, which is the following Limbladian L. And without actually getting into too much detail about its structure, what's important is that it defines an equation of motion, where the evolution of the density matrix is governed by some matrix exponential. Now, under relatively mild constraints, this Davies generator satisfies a condition known as detailed balance, which for all intents and purposes just means it fixes the Gibbs state. In other words, we know this algorithm will eventually converge, we just don't know how long it will take. Now, to attempt to quantify the convergence rate of this process, I need to introduce the concept of a mixing time, which simply put is the amount of time it takes for the distance between any two states to half. And generically, there's not that many ways that we know how to analyze mixing times for quantum systems. But a first approach is known as a bound on the spectral gap, where the mixing time of the process has an upper bound, which is given by n over the gap of the spectral gap of this Lindbladian. And inherently, there's some polynomial cost or polynomial overhead in the system size. A much more refined bound is what's known as a modified log Sobolev inequality, where MLSI, in some sense, quantifies the rate of decay of the relative entropy between the time-evolved state and the desired Gibbs state. And here in the top right-hand corner, I've put the definition of the quantum relative entropy. Now, this rate of decay is always negative, or in particular, non-positive. But if you could actually show that it's bounded from above by itself, that would consist of a log Sobolev inequality, or modified log Sobolev inequality, which in particular implies an exponential decay of the relative entropy. Under some standard entropic manipulations, this also tells you that the mixing time is upper bounded by a polylog factor in n, which is a phenomenon known as rapid mixing. Great. So to warm up to our analysis, the starting point is really to look at what we can prove for the simplest Hamiltonian in the family, which is just, again, this non-interacting sum of single qubit Pauli Z's. And again, the Gibbs state associated to this Hamiltonian is a simple tensor product. Under our framework, we can write down the Lindbladian of the global system in terms of a simple non-interacting sum of single qubit Lindbladians. And the whole evolution is decoupled. Now, I'd like to convince you guys that this is arguably the simplest Lindbladian you can ever write down. And using a brute force calculation that I won't bore you guys with, you can show a log Sobolev inequality for this family for this specific Lindbladian, where the so-called MLSI constant is just a simple function of the temperature. And as a side remark, it's kind of intriguing that in the previous talk, there was some component of a reduction to like a depolarizing semigroup, which is in some sense what's going on here too. Great. So now the kind of key motivating question behind our analysis is, can we inherit the fast mixing of the non-interacting case to the case which is in some sense conjugated by the circuit? And here, the key technical idea is to look at our Lindbladian in a basis rotated by the circuit. And the key technical claim is that we can write this Lindbladian as a convex combination of two other Lindbladians, one, the simple non-interacting system we all love, and the other one, an arbitrarily complicated other Lindbladian L rest. However, we know that both of them satisfy detailed balance, so at least we know one of its fixed points. And here, the convex combination constant Q is just a function of the locality of the Hamiltonian and not the system size n. Now, under relatively standard entropic manipulations, we claim that this convex combination claim actually lifts your MLSI for the global Lindbladian L, with now a constant which has been damped a bit, but only still a function of the convex combination constant Q and the non-interacting constant alpha and I. Unfortunately, I don't really have time to dive into the proof of this idea or this claim, but I'm happy to take questions too. And I should also say that we learned about this convex combination idea from a very nice paper by the Izard group, who did a very similar calculation, but for the spectral gap. Great. So I wanted to just pose some future directions and highlight some of my favorite open questions. The first one is on the BQP hardness of constant temperature Gibbs sampling. And here the question is, can we embed a generic quantum computation into a high temperature or constant temperature Gibbs state, which is essentially one of the same questions posed by Gibbs in the last talk. It turns out that this is quite delicate because there's some deep connections to hardness of approximation and the quantum PCP conjecture. The second question, which is closely related to our note on quantum advantage, but with input noise, is whether quantum advantage can be achieved with noisy constant depth circuits. Now here, the question is there a family of constant depth quantum circuits which is classically hard to sample from under depolarizing noise in every gate? And the statement here is about quantum circuits which do not have access to classical feedback. It's just a quantum computer operating entirely by itself. And in some sense, this is really asking a deep question about fault tolerance with low overhead at constant depths. And with that, I wanted to pivot to questions. Thank you very much.
Lots of time for questions. Do you want to?
Thanks for the great talk. I have a question about your one to last slide. So can you give some intuition about this rotation, which allows you to write your Davis generator as a function of the Davis generator for the free evolution?
Yeah, perhaps I should have gotten into more detail given the time constraints, but the broad picture is that this Lindbladian is a second moment of the jump operators. And so if you can write that second moment as a convex combination with some additional detailed balance properties, then that's essentially enough to argue that you're always making progress. In some sense, what we're saying here is that there's some global Markov chain, but some component of it, or some component of this convex combination is like an all-to-all walk on the hypercube, which is this non-interacting thing.
Yeah, thank you.
Thanks for the talk. I hope to ask that, is that possible to show similar this quantum advantage in Hamiltonian more relevant to analog quantum simulator, like Fermi-Hubbard model? Or do you think there could be a chance to study this kind of question?
Yeah, that's a fantastic question. You could try to envision a fermionic version of these Hamiltonians. You may need to come up with some circuit model of computation, which is hard by itself.
Oh, thanks for the great talk. Is there any classical counterpart of your concavity claim?
Yeah, surely. I don't have an immediate reference in mind, but there's a short proof of this in the paper, which I'd refer you to. And it just works analogously for classical Laplacians.
Okay, thank you so much.
If there are no more questions, I think let's wrap up the session and thank all the speakers again.